So welcome everybody. My name is Sebastian. I work at Linksoft. I'll be hosting this Docker and web service introduction workshop. And this microservices at your service project, you'll hear a little bit more about in a short while. There, I was hoping that slide, right, that works. So the schedule for today, I'll do a little bit of introduction to tools and terminology. Then we'll walk through an example, and then we'll have a 1 hour break. You can do what you like in that break. I'll send the slides already in the break in case you want to take a look at things already then. Then after the break, we'll walk through another example, and then we'll finish off with a short question and answer session. Then on Wednesday, we have a follow-up to this. But we don't have much planned. We hope to be here in case you have problems with the examples or with Docker, and we want to be here and try to help. I give no promises that we can help, but I know that I've been a beginner many times, and in the beginning it's kind of helpful to have someone to ask. So we'll be here mainly for that. We might also do some short presentation of something that we didn't have time to present today. I'll resend the invitation for that day so that you remember which link. But then we'll jump into the main presentation. So this is the world as we know it. We have software as a service, we have platform as a service, we have infrastructure as a service, and in these abbreviations, SaaS, PaaS, and IaaS. And we have large international organizations that provide this type of services. And more recently, we have also gotten the European language grid, which is a European Union funded alternative to these existing organizations. And the goal of ELG is to become the primary platform for language technology in Europe, both for non-commercial and commercial language technologies. And this is where our microservices at your service project comes in. We intend to identify, oh, sorry, I should present the consortium first. So this is a European Union co-funded project with Linksoft, Gradient, University of Tartu, and Reykjavik University. And our objectives are to identify suitable open source NLP tools for example, this European language grid. And to be able to share them in a good modern way, we intend to Dockerize them. This also makes it easy to share to ELG, but also on similar platforms. Every platform has a little bit of tweaking needed, but the basis is good to have them Dockerized. And then we also plan to share information about our methods and results. And hopefully people are starting to use the tools that we find via ELG or some other web service. So today we'll focus on the objective 2, Dockerize the NLP tools. And this actually consists of 2 main steps. The first step is to add a web service API to the tool. And the second step is to create a Docker image for the tool. The rest of the steps in this whole process is here 3, 4, 5, and 6. We'll not go through them today. But 3 and 4, they are not very time consuming. I would say a day for the instructions and half a day for the Docker image storing. And then number 5 depends, I guess, on your tool. Couple of weeks is reasonable. But we have also had a long project for 9 months of integrating our tools there. So it's a bit of planning and depends on your tools. And then finally, we intend to list things or the Docker images on this LREC share repository because we don't want only these tools via ELG. It is also possible to use them via other web providers. So then we'll start with the real workshop material. And before the workshop, I shared this with you. I hope you have tried. So to be able to test the material that we provide in this workshop, you need to have Docker installed. And if you're advanced, then after our examples, then you probably want to try some tool of your own. Perhaps you have developed something yourself. And I should also, it's not a warning, but I say that this workshop is aimed at getting beginners started. So if you're not a beginner, you're more than welcome to stay. And you're more than welcome to come and join us on Wednesday to assist us with helping the beginners. So the target of this workshop is to introduce you to some terminology and tools, give you some links to more material, and then hopefully you are prepared for trying it yourself. If you get more serious with this, then you will soon enter this list of things that we won't have time for. But I'll make a small parenthesis here. For example, memory. You want your image as small as possible, because if you need to host many images, then you will soon run out of space. I'll give you an example. When I packaged our machine translation the first time, I ended up with an image that was 10 gigabytes big. And our software engineer said, whoa, and then they fixed it, and now we're down to 400 megabytes. And if you need to have hundreds of these, then you very soon, this memory consumption very soon becomes a real problem, both for your wallet and the environment. Then if you have real-time things, we'll mainly talk about REST API today. And if you have real-time things like real-time speech recognition, then you probably want to look at other alternatives than REST, for example, WebSocket. And if you don't know the difference, then Google it or ask your engineering crew. And I don't say Google it to be arrogant. I'm not very good at describing the difference. And then more and more language technology tools, they rely on GPU. And NVIDIA has made an extension that allows you to use Docker also with GPU tools. Another thing we discussed a bit was security aspects. Is it safe to use Docker? It's not more or less safe than anything else. As a beginner, you should be aware that if you share an image, you probably also share everything that is on that image. So if you have data on the image or models on the image, you can consider them publicly shared if you share the image. There are ways around that, but as a beginner, that's how you should think about it. And in the open source world, this might not be a problem. It might even be intended. And then we have the Docker Hub. It's like GitHub for Docker images. So if you want to share your images with the world, then a Docker Hub is a good place. And finally, if you are the European language grid, or if you design your own platform as a service platform, then you probably need something like Kubernetes to organize this Docker images and containers into a fantastic software architecture. And all these web services that I mentioned before, they're doing something similar. So ELG is using Kubernetes. I don't know what the other organizations are using for real. Then we'll start here on the software as a service. I'll move this little guy here. And software as a service, it means that you don't have the software yourself on your machine, but you access the software via a web service, via the internet. So that's the software as a service. And on the one end, on the back end, you have the real tool. And on top of the real tool, you have a REST API, and then which sits on a web server. And then people can call this API from other computers in the world via a client. And if you look at the REST API, then it has an endpoint, which is an HTTP address, usually many. Then it has methods defined what the client can call. This usually is a post where, for language technology, you would send, for example, text or a file to the backend tool. And there are other methods that does other things. For example, which version of the tool is it? Is the service available? Things like this. And you, as a REST API developer, needs to document which methods are available and how you need to call these to get the results you need. So in the client, then you follow these instructions, and you put up a sequence of call often. For example, the first call might be to send your password and username to get access to the service. And there are about as many tools to make these calls as there are programming languages. We'll use Python and curl in this workshop. Curl is a command line tool that is very often used to give short examples for calling REST APIs. So it's good to know a little bit about. The general call structure consists of headers, data, method, and address. So I have an example down there. Curl -h. So -h is a header. In this case, you have an authorization header, and there is a $token there that you probably received in a previous call. And then there's a second header about the content type. And then there is a argument for sending some data, in this case, a file. And finally, then there is the method, the post, and then the address. So if you send this, then in the best case, you would then receive a translation back of this SUM file. Oh, and there. So doing this yourself is surprisingly simple. This API stands for Application Programming Interface. So that means, as we saw in the previous picture, that it's just an interface and you need some tool behind it to actually do something. And once you have this tool, then you can add your REST API. And there are many common practices and good guidelines, etc. Every organization has their own specs. And for example, ELG has quite good, simple specs for what you need to do when things go well and things go wrong. What message do you need to send to the client? And there's standard codes for this as well. You probably have seen this 404 not found sometimes when you surf around. And then there is this Python Flask package for implementing this REST API for your tool. And there is, again, probably one package or many packages per programming language. We use Python here in this workshop. And ELG has even made an SDK using Python Flask that should simplify for you to make a tool compatible for ELG. This won't take 45 minutes, but sometimes short is better. Then we are coming to the point where we can Dockerize things. And Docker is basically a software for packaging things into small virtual machines. They're not necessarily small, but they're sort of virtual machines, I think of them at least. And you package them into an image, and this is the image you can then share for others to use this virtual machine. And when you use it by running a container of it. This Docker method makes it very easy to install tools with different dependencies or different operating systems on the same host machine. So it makes it easy also for others to install and use the tool. For example, in the scientific community, you have these yearly challenges in parsing and machine translation. And you could, for example, ask the participants to submit this system as Docker images. And that would help comparing to these systems for the next year or for another data set a while later. Or you could use it to share software development examples for your students. And it also makes it easy to create microservice architectures. Like in the case of ELG, it roughly looks like this. It roughly looks the same in Linksoft's tools, where you have these jigsaw puzzles that are NLP components in a Docker container. And it makes it very easy to put together many different containers with many different things in them. It's easy to replace them if there comes a speech recognizer that is better than the old speech recognizer. And if you're advanced, then you can use Kubernetes to orchestrate these containers. And what Kubernetes helps with is that if if you, for example, your ASR container can only serve one user at the time, and you get 2, 3, 4, 5, or 10 users at the same time, then instead of sending these users a timeout message that the service is not available, then Kubernetes makes a copy of the container and duplicates it so that it allows running many side by side, provided that your host machine can have more than one. So then we get closer now to the practicalities of the Docker images and containers. So to start with, you need to install Docker engine, as I said in the pre-workshop slide. But once you have that, then you can start. And usually you start by getting a base image usually from the Docker registry. And if you're familiar with Git, then the syntax is pretty similar. So you pull an image from this Docker registry. And once you have the base image, then you want to install your own tool on this. And you do that by creating a Docker file. It's just a text file, basically, with a list with a list of instructions. So tools to install, commands to run, like cd to this directory, compile this, run cmake in other order, but that's the thing. And then at the end, maybe you want to remove things that were unnecessarily to keep on the image. And then once you have this Docker file with a list of instructions, you use a docker build command to compile this into a distributable image. And then this image would sit on your system, and you probably want to test that it does what you intended. So then you run a container from it. And then that should then work as you intended, whether you have a text tagger or a web demo or whatever. And if you're happy with the image and you want to share it with the world, then you can publish it on the Docker registry. And it's free to get an account there if you share the images for free. So if you share open source tools, as far as my research says, then it should be free to create an account there and publish your images. Then we are presenting the sort of command line commands. I'm not sure if there are alternatives really. But there should be equivalent functionality to get from if there are other clients. So one useful thing is the Docker image list or Docker container list that will show you which containers and images that exist on your machine, and a bit of information on them, for example, how much memory they take, or if they're connected to some port, if you have a web service, for example. When you're beginner, you will probably notice that you will end up with many half-baked images that are dangling in your system that are not really needed but take up space. So it's a good practice to check occasionally how much space you have filled up, either intentionally or by accident, and then remove the things that you don't want. If you have a running container and you want to delete it, then you first need to stop it, and then you can delete it. And we touched it briefly, the Docker run, how to make a running container from your image. And then everything that is on the container is local. So if you delete the container, anything that is on the container, any data, any models, etc., any trained tools will be deleted when you delete the container. So what you often do is that you map a local directory on the host to the container, so that everything that is in this local directory is also on the container. There's a sort of symbolic link between them. And then you can have, for example, you can have your models on your local machine, or you could store data into a database on your local machine, etc. And there's also an option, publish, that you map a port from the container to your local machine. And that would then expose, for example, a web service from your local machine via the container, or via your local machine to the container. And we'll see examples of that in a short while. And then when you have a running container, you sometimes want to hop onto it and see what's happening in there, maybe fix a few things. Then you can, for example, do Docker exec or attach. Then you hop onto the container. And you get a bash prompt in the Docker exec example. In the attached, it depends a bit on how you do it. You might end up with just seeing your tool running, for example, spitting out output. And then when you're done and you want to hop off the container, then you need to exit it in a, say, graceful way without deleting it. Then you have Control-P, Control-Q. Control-D probably also works, but my experience, I thought it would sometimes kill the container. So you need to practice a little bit, see what works for you. Could be that I'm wrong. And I believe that was actually all I had. I think we'll allow a short question and answer before we move on to Filip's example. So if there is anybody that would like to ask a question, please go ahead.
Is Juhani's example next?
Juhani's, sorry. Then I think we jump straight into Juhani's example.
Hello, I hope you guys can hear me. Let's share my screen. Let's start with this one. What I have for you is I'm going to walk you through a very simple example of a Docker container with a Flask application on it with both a web user interface and a simple API which is to be used from the command line. Maybe I should show you the application itself that we are wrapping in this Docker container. So here we have a nice little website which allows us to test Finbert neural language model. How it's done here in this example is that we have an example sentence, and one of the tokens is replaced with sana, which is Finnish and basically means a word. And once we query it, we get the predictions from the language model. For example, here we have a most probable prediction would be ohjelma, and it really fits well with this sentence. It goes like this in English. During this weekend, what's Pääsiäinen? It's Easter. Yeah. We have an Easter party which includes a lot of program and goodies. So this is the application that we are running in our Docker container, and basically we are wrapping a language model into this Docker container, which is queryable by the user. We also provide an API for command line usage. So here we have our little folder structure. In Flask, the thing we have a folder static, which contains basically all the static static files we need for our application. Here we have this simple PNG image you saw earlier. Another important folder is the templates, which contain the HTML templates, which we will look closer in a little while. The other important files are the Docker file itself, which we use to build our container, and the application itself. I think we should have a look at the application itself. Yeah, here we can see that. Can you see the screen? Probably you can.
Yes, we see it.
Okay, good. I was just afraid because I moved it a little bit. Anyways, we can see here from the size of this program that Flask is really simple and easy to use. I guess you would call it a micro framework or something. Anyways, what we have here are the imports. Here we are importing our query tool for the language model. We do some kind of basic settings. For example, our application root is the root itself. Here we load the Finbert language model directly from a repository, so we don't have to include it in our Docker container while we are building it. We have three sort of addresses that our little web application responds to. The first of them is the root folder. What we do here is simple. We render template. Basically, we give out the index.html with its parameters. The parameters in this case are simply the application root. The next address that we respond to is it's what we call when we want to have our predictions in our web user interface. This is still very simple. We get our language model, which is global, which we defined here. We get our input sentence from the JSON request that we received with this post query, and we give error messages if there are nothing to be predicted, or if our input sentence is too long. Finally, we get our predictions basically straight from the library itself. We give it our input sentence and get the top 10 predictions. We render our predictions into we give our predictions into the render template method, which gives us our results in HTML, and then we return our predictions as a JSON response, which the index.html takes care of. We also have a very simple, simplified version of the predict address, which is basically meant to be used from the command line. Here we again get our language model. We get our input sentence from the request, and we put it again, get our predictions, and then we return them. Flask also has a nice property that it contains a web server of its own. Because it's the simplest way of getting this done, I went with this here. But if you are doing something more complicated, you might want to run a real web server inside the Docker, for example, Nginx or something. Anyways, we are running our web server in IP 000 and on port 8866. As we can see from the result.html template, which was used here, that Flask has a fairly expressive and powerful templating engine. For example, we can use for loops, and here we use for loop to create our small table for results, which you can see in the web user interface. Maybe I should show how the querying from the command line works next. So here we have a typical command line, and to use our command line interface, we use curl, and we send a post request with the data sentence in equals, and here we have our query esimerkiksi sana on viime ollut esillä, and finally our address. I have this Docker container already running, so this should work, and it did. So, for example, what's this? Tämä homos, cannabis, se, pakkoruotsi. These things have been, I guess, in the news lately, according to this language model. But anyways, we see we can get predictions out of our Docker container using the curl command. I guess next we should go through how the container is built, how it is being run, and how you can run it in your own environment. So here we have a very simple Docker file. As was discussed during the previous presentation, Docker containers are built using a Docker file. Here we start from an image of Ubuntu 18, and once we have our base image, we start installing the software we need. The software we need for this container is firstly Python 3 install tools and the development headers for Python 3. Next, we update our just installed Python package install tool, and using the said tool we install Happy Transformer library and also Flask library for Python. Since we are running our application on port 8866, we expose the port to the world. This in practice, this means that our container has this port open and we can communicate with it. Finally, we copy our local folder into the container, and really finally we define the command which is being run in our container. Here I'm running Flask's inbuilt web server, but as was mentioned earlier, this is not the only way to go about this. And for more complicated examples, I would recommend you to run a real web server. So once we have our little Docker file, we can build our image. I've done this already in this computer, but the command to build this container goes like this. It's docker build and our tag and context is this folder. This was really fast because I just did it. If I would have not done this 5 minutes ago, this would have taken something like maybe 10 minutes, mostly due to installing the software. So now we have our image built. What are we going to do with it? We are going to run it in our local machine, and the command to run it, we can, yes, here, docker run D here means that we are running it in detach mode in the background. Here we define that on our local machine, this IP and port pair is paired with this port in the container itself. And the image we want to run is Finbert demo, which was tagged here during building. So I'm not going to run this because it's already running on my local machine, as we can see here. Here we list all our running Docker containers. We can see the ID, image ID, command running, and how the ports are mapped. Oh, what else do I have to say?
Can I say one thing there?
Yeah, go for it.
In your name, then you have exciting Hofstadter, and that's the default. If you don't give a name, then Docker makes it up.
Mm. Yeah, I guess you could add names. Do you remember how it's done?
Yeah, it was in my slides. you just, when you do Docker run, then you just add, I think, -- name. And
let's give it a go. I guess we can show you how to kill these Dockers as well. Let's stop our container. And so name like this, right? Let's give it a go. No, I'll just Google it real fast. No, it should be like this. It's gonna be last. Yeah. Yes, now we can see we have a same name for our container. Oh man, it seems like I'm way ahead of the schedule, but this basically is all I have to show you guys. Maybe we can show you how you get the shell into the container.
Yeah, that's a good idea.
I'm just going with like how this goes. Docker exec. So it's like I guess we can use name here, right? Welcome to demo. If not, we'll use the container ID. Nice.
Yeah, you're getting very close.
It works now, right? So anyway, now we have a shell into our container, and we can do whatever we want. Basically, we can edit the. No, we here. Maybe not. So now here we have our little Docker file, which is copied inside the container. And similarly, we can look at our our application itself. And I guess we can have a look at what's running in our container. And so this is a kind of a simplistic example in a sense that we are downloading our model during the startup of this container. So I guess in a more complicated example, you would have the model in a separate volume. But I guess that's out of the scope of this little demonstration. Hey, I'm sorry, I don't have anything else. That's it. Do you want something to be made more clear or something?
I think that was good for me. I'll leave the floor for the audience in case you have any questions.
Can I ask a question?
Please go ahead.
It's not quite clear to me what the purpose of exec is. I mean, why would you want to go inside the container and look at the Docker file? I mean, if you were to have to change something, wouldn't just build the Docker image again?
I mean, you might have some debugging needs, for example. I would imagine, except for development needs, I would imagine this could function as a kind of way to also give commands to the container, especially if you're not running it in an interactive mode.
I can give examples how I have used it, for example, and it's basically during development and debugging. So I noticed that my machine translation web demo was very slow. Then I jump onto the container, I disable the true casing, I jump off and I try the web demo again without rerunning the container. And I noticed that it's much faster. So I know, all right, good. Or you can hop into the logging that this web demo spits out, and you see, oh, the backend machine translation wasn't available. Things like this. So it's during development and debugging, basically.
Okay. Yeah.
Yeah, it is also a useful way to get a throwaway machine. So if you just want to test something safely, anything really, then you can just start one of the ready-made images, and then you do what you do. You get a shell, and then when you are done, you simply wipe the image, and that's it. So it's a really easy throwaway machine. I would also imagine this could be something you could use when teaching, if you want to give access to students to a machine, but you don't want them to kind of step on each other's toes. Then this is also an easy way to get a throwaway Docker image or, well, container.
Okay, very good.
Any other questions?
Maybe it's early lunch.
I have another question, Hector here.
Yes, please.
Regarding some of the tools we are going to use for this project are more complicated than this. I mean, they have many functionalities, different parameters to call them. So, which is the best way to send that information to the web server?
I guess Filip's next example is way more complicated, and maybe that will shed some light. But like you can use like just REST API for very complicated things, right?
Mm-hmm.
Yeah, let's see in the next example, Hector, if that sheds some light on your question. Otherwise, feel free to ask it again, and we'll see if we have a better answer. I have one comment though. So Juhani mentioned something important here. He said, I ran this 5 minutes ago, and now it's this fast. And Docker does very heavy caching. So if you run things once and then you just change a small thing, then it will try to be smart and only change the small thing that you changed. And then things go much faster. Otherwise, it takes just as long to install all the tools that you need as it does in real life. So if you have an Ubuntu 18 in this case, and you want to install many dependencies and compile many things, then it will take many hours to build. So I'm glad, Juhani, that you thought of this before and didn't spend 10 minutes on compiling.
Yeah,
we're
the
lucky.
startup is also would have taken like 5 minutes.
Yeah, exactly. Running the container can also take quite a while, depending on how many things you give it.
Yeah, since we have a little bit of time, maybe I can step in and tell a little bit more about the caching. But if you could, Juhani, let me share my screen.
Yeah.
Just to explain how the caching actually works, because it's really good to understand. So I'll just, this is going a little bit ahead of time. This is something I will be showing after lunch, but this would be your typical Docker file, maybe slightly more complicated than the one which Juhani had. But you see that basically every line in this Docker file is a command of a kind for Docker to run in the image. And they have this concept called layers when building the actual image. So what happens that every of these commands, as you run it, sort of it changes something in the image. It adds files, it removes files, it just changes the state of the image one way or another. And when you saw Juhani as he was building the actual image, it produced a line of output for every line of this Docker file. So the Docker just goes line by line and executes exactly what it should be doing. And after every command, it sort of stores as a cached information everything that has changed in the image, and gives it this hash identifier and caches it. So, you know, if you install there a 5 GB file, then it, you know, just copies the 5 GB file into the image and stores that as a layer that can be cached. And next time you run the image, or sorry, you run Docker to build the image, it again goes from top to bottom and checks whether something has changed. So if I now do not change anything on the first 10 lines, it will notice that it has already cached this sequence. So it has cached these layers one after another and simply applies them, just grabs them from the cache. And the moment you change something, so if I now, you know, just do some, no matter how minimal change, I just add a parameter here or something, it doesn't matter. It means a change. So at this point, Docker realizes that, okay, it doesn't have a layer cached for this step. And then it just executes the command so that it learns which files have changed. And what's important to know is that after this point, none of the caches anymore apply because something has changed in the image. So you cannot anymore be sure that anything that you cached after that point is valid. So after that, it starts to rebuild the cache again. So the order in which you do things in Docker from the caching perspective actually matters. So if you know that, for example, in here I have like install pip and then install requirements of the example I will be showing, and this install takes easily 10 minutes because it needs to run all of the pip install, it needs to compile things and so on. It takes kind of 10-15 minutes to do. Then I like to have this as early as possible in the Docker file, because as I'm kind of debugging when I'm preparing all of this and debugging, I'm probably debugging somewhere here towards the end. And every time I rebuild the image, it grabs from cache the layer with everything pip installed and compiled. If I had that late in the Docker file, basically every time I change something, I will end up reinstalling everything with pip. So most important thing here is to remember that one line in the Docker file corresponds to something that can be cached, and anything after a point of change to the end of the Docker file needs to be recomputed when you rebuild the image. So this is something that you might want to keep in mind so that your debugging sessions do not take too long. That's all I had to say about the caching. I'll share my screen, and the idea here is to show you how to Dockerize the Turku neural parser pipeline, which is a neural parser that has gained some user base and some popularity. And I don't have time to walk you through all of the details, and they also keep changing all the time. But what I have done for this workshop is that we have slightly rewritten the pipeline to make it easier to run and provide it with a little bit more sane requirements file so that it's actually possible to install it, which started to be quite difficult over time because it depended on some packages that were quite outdated. So theoretically speaking, you should be able to basically run all of the commands I will be showing in this session, but in practice, some of them take quite a while to run. So I don't think we'll actually be able to fully achieve that. It's mostly when you are installing the requirements, then it needs to compile things, and it might take a while, especially if you have a not so strong or not so powerful computer. But I will show you basically everything that I have that you need to know about how to run this parser, and that would be maybe in a way a starting point if your job is to sort of Dockerize it, is in this Colab notebook that I have created. So I'll just copy this and put it into chat. Just a little moment. Here is the chat. So you can, there we go. So you can just click that and it should open you the Colab the way I have it in here. And what you will see is something like this. So this is basically a mini tutorial on how to run the parser pipeline. And it basically follows the steps that we will need to follow when we are creating the Docker file for this parser, and when we are creating the API that we want to run. So the usual, you clone the code. Right now it lives in a separate branch because this is a very fresh software that I'm showing you here. So you clone the branch, then you cd to the directory where it got cloned. Then, as usual, you install the requirements file. So then it pulls everything that this parser depends on. You see that it's pulling most significantly Torch, which takes a while to set up, and everything that Torch depends on. And then it will also install things like the UD pipe tokenizer, which does take a while to compile and it does some complaining, but these are not very serious complaints, so we don't have to worry about them. Basically, this is what you need to do when you want to run the parser. You get the code and then pip install the requirements, and then you need to fetch the model which you want to use to parse. For the latest version of the parser, we have only one model available now, and that's the Finnish one. So FITDT dia is the name of the model, and this is just a little script that comes with the parser that if you give it the name of the model file, it knows where to go and where to fetch it from, and does that. That does take a while, because the model files nowadays pretty much always contain a copy of BERT, which is in itself half a gigabyte. And then if you want to parse in the parser, this is basically the Python library interface. It's already super easy. You basically, every model comes with different pipelines. It's maybe not super relevant here to go into the details of what that means, but you just load a particular pipeline, and in here, it's parse plain text. So that basically says that you will be asking the parser to just parse plain text, just receives a string, and then it parses it and tokenizes and does everything it needs to. And once you've got the pipeline, so that's an object that has all the BERT and everything is loaded. So that's an object you want to hold on to. That's not something you want to reinstantiate between calls to the parser, because it takes maybe 20 seconds to load all of the models before it's ready to parse. So this is something you want to do only once. And then you can parse text, just p.parse and give it a text, and you get the output of the parser. That's already quite fast. Once the model has been loaded and initiated in the memory, then everything is already surprisingly fast. And here is the output of the parser. For those who understand Finnish, then you can see that it did something quite reasonable. It recognizes subjects and so on. There is no morpho tags and POS tags right now, because this branch of the parser is still a bit in development. So what it gives you right now is just the dependency tree in here. So this would be the thing that you kind of get, and you need to make a little API for, and you need to dockerize, and that will be basically our task in the remaining 25 minutes that we've got. So let's first have a look at the API. So I'm using the same as Juhani, so I'm using Flask to do that. And in here, I will just show you a little bit how you pass parameters into Flask, because, for example, we could have different models, right? And right now I have Finnish model, I could have English model, I could have some other model. So I need to tell it somehow how to, or which model to load when it starts, and which pipeline to load when it starts, because I could be using different pipelines. And there is also a parameter that allows the parser, or tells the parser to cut the input after a given number of characters. This is quite useful if you are running something like a parser as a public service, because sooner or later you will notice that people on the net start cut and pasting whole books into this little demo parser that you have, and then it crunches a book for maybe a day. So you want to make sure that people do not misuse whatever public service you have. So we have basically 3 parameters we need to have when we launch the parser. We need to know which model, and we need to know which pipeline from the model, and what is the maximum number of characters we are willing to parse before we kind of cut the input. And it's actually quite difficult to pass command line parameters into Flask. I never quite figured a way that I would have considered very clean. So my favorite way to communicate parameters into Flask is through operating system environment variables. So you can just, define variables in your shell, and then when you run a Flask, then it reads the variables. And that, I think, is at least for me, the easiest way to communicate these into Flask. So it's in Python as simple as this. So you just know that, okay, I'm working with some variable TNPP model, which is where I let the user specify which model this should be loading. And it's always good to provide some reasonable default value. So here I say models fitdt pipelines.yaml. Parse plain text would be the pipeline, and then TNPP max cars, I just put there 15,000. So I always get this variable from shell, possibly the default, and remember these in these Python variables. And here is the 2 lines that you saw in the Docker, in the notebook. So that's basically the way how you start the parser. Here you tell which model, and here you tell which pipeline, and you get this object P, which is the actually loaded parser. And that is something that you do only once. So you see that I've got it here at the beginning of the module. And that is what sort of happens when Flask starts this, this whole thing. And then we have these different requests that we want to react to. And we want to react in 2 ways. We want to react to a normal GET request. So that just means that somebody, types in the URL of where the parser is running, and maybe wants to give it some text to parse. So this would be the sort of, you have some URL of the parser, and then you say, okay, the text I want to parse is something like this, and here is some text. So that would launch a GET request, and when it receives a GET request on the main path of the URL, on the root of the URL, this function gets called. And this is how you get the text out of the request. So there is a particular way how this is done in Flask, and it's this exact way. So when you do flask.request.args, you get a dictionary which has the arguments from the command, from the URL. So if I have here something like $text equals and the text, and then I don't know what else I could have there, some maxchar equals some number, then I would have in this dictionary in here also maxchar as a key. So Flask sort of parses the request for you in here, and there is not really very much to do. So if there is not the text provided, so if the user just types maybe the parser main URL, puts a slash there and hits enter, then you have nothing to parse, but you don't really want to crash at this point. So you just check that if I do not have any text, you notice that here I use get. So if there is no text in the URL, I get none. So if there is no text, then I just say, okay, I return the user a little friendly message and give an error code for the browser. So this says that this was an invalid request. And if I do have a text to parse, then I just parse it, assuming that nothing crashes. In reality, you would probably want to have a try except around this call. And if I'm like happy with the output, then I just return the result, say that the type of the returned response is text plain and it's UTF-8, so that the browser can correctly display the output. And then I'm pretty much done. And the default code that it returns is OK200, so I don't need to say that. So this is a simple way to react to GET requests, but because this is a parser, so you can assume that people might be asking you to parse relatively long documents as well. So you also want to support the post method. So this is the other way in which you can submit data to a web server, which this basically becomes. And this is an example of how that is done. So you receive your data in here, Flask request get data as text. So it gives you a string which has the request as it was submitted to you. And let's just simply assume that the only thing that the user here ever needs to give you is the text itself. So you can simply use it directly. Quite popular way at this point would be to assume that the request is actually JSON data, and you could just submit as complicated thing to the parser as you wish, and make sure that it's encoded in JSON, and Flask is perfectly capable of working with that. And it can decode the data for you on the fly, and then you basically get back an object which has all of the information that the user has given you. But here, all we need is just the text. And here we can then cut the text to our favorite maximum character. And I think this will actually crash because there is this args.maxhar, sorry about that. So let's just fix this. And again, if you do not get any text, then you give an error message and some error code. And otherwise, you return the parsed text and give that back to the browser that asked, or whatever tool the user was using to submit. So this is, I guess, the absolute minimal way in which you can implement a very simple API that talks HTTP and reacts to both get and post requests. It's actually really not much more complicated than this. And the way how you can communicate things like the loaded pipeline or so into these functions that react on the web requests is through global variables, because what goes in here, in these parameters in here, is actually request specific. So there is not like a global parameter. So here you have to communicate through global variables. So this is basically the API. This is something you could run with Flask run, and it would work. And now we want to yet add this Docker on top of it, so that you can actually wrap it into a nice image that you can then distribute to your users, or launch million times in some cloud. So for that to happen, you need to have a Docker file, and here's a Docker file for this particular version of the parser, and it tries to achieve basically everything that I have shown you. It tries to achieve as a sort of instructions for Docker to build, and I try to put here few extra things which Juhani didn't have, so that we see how these are done, because there is usually some amount of Googling behind this. None of this is like rocket science. All of this is actually quite easily Googleable, but there are always few kind of things that you can stumble upon, and then it might be useful to have a worked example. So first of all, we start with some base image. That's pretty much what you always do. And a good image to start when you have just basic Python code is the official Python image, Python:3, unless you have a particular version that you want for a Python. If I wanted this to be based on Python 3.6, and it would be somehow very important for me to be the case, then I would say Python 3.6. But because I'm fairly agnostic which Python this runs on, providing that it's Python 3, then I just say Python:3. And then you always set the work directory. So that's basically where Docker's within the image, where Docker starts putting stuff. And if you Google the Docker documentation of the Python image, then it tells you that you should be putting stuff into user source up. For some reason, I just do what they say, and that's it. So then there is this one thing that I think is quite important, and that's to use virtual environments. If you do not use the Python virtual environment, then you might start getting various strange error messages when you run pip install within an image, because it runs as a root, and pip complains quite a lot when it's run as a root. So I found that it's much better to actually make a virtual environment. This is somehow also like a core habit that I have developed. Anything I run in Python, I always make a virtual environment for it, so that I know that things don't sort of step on each other's toes. And there are a few things that you need to do to make that happen. So this is just a variable, environment variable, which I defined. Where is the virtual environment? So I just call it virtual env and come up with some path. So user source up venv tnpp. Then I make the virtual environment the usual way you would do it in Python. So Python module venv and then the name of the virtual environment. But here is a little difference. If you were just running this in normal command line, at this point you would say that the venv tnpp /bin/activate. But it doesn't really work in Docker, because every command it runs in a separate shell. So if you go and read what this virtual environment /bin/activate actually does, it really, the most important thing that it ever does is this one line. It basically sets path variable to be virtual environment /bin, and after that anything else. So when you run Python, it picks the correct one from the virtual environment. This is really kind of everything that you need from the virtual environment bin activate script. So I just grabbed that. So I just set the path variable to point first to the bin directory of the virtual environment and then to anything else that was in the path variable. So this is basically a poor man's version of virtual environment activate. And now we are done. This would be the basic Python setup that I would recommend for Docker. Start from a Python image and then install and activate a virtual environment in some place. And now you have to remember that the way Docker works is that it lets you pick files from the build environment, which is usually just the directory where you launch it, and then you copy them onto or into the image. So first thing I need to copy is requirements.txt. So this is what it does. It just copies the requirements.txt file into the image, and then it's there. And remember that I am in this working directory on the image. Then once I have requirements, then usually the first thing I do is that I upgrade pip. That often kind of prevents a lot of troubles from happening, and especially if you are on a bit older machine. And then I install the requirements. So this would be something that you would generally do when you run something. Then you could have, of course, done git clone the code. That would mean that the image would always be based on the latest version of the code. I rather chose to copy whatever I need to copy into the image. Here you might want to be quite selective. You don't want to copy absolutely everything you have in the directory where you currently are, because there is usually a lot of other junk you actually don't want to distribute with the image, and that makes the image large. So I know that to run the parser, I basically need to copy over the requirements. This is something I've done already. And then I need to copy over all Python files and the tn parser module. Because if you look into what the parser directory structure looks like, then it has a bunch of top-level Python scripts, and then it has tn parser directory with the package tn parser. So I just copy those. It takes a little while to get right where you put which slash, so that things get copied into the correct place. And when things don't work, then when you start an image, then you might need to attach to it and see so what exactly got copied where before you get these things right. But basically, if you want to recursively copy a directory, this is the syntax to do it. This is the directory name followed by a slash. And where do you copy? So in the work directory slash, and you repeat the name of the directory. Otherwise, it will copy all files flat into the Ceres app directory. That's just the way Docker works, so we have to live with that. And now here is a thing which I don't think Juhani had in his Docker file, and that's how do you pass arguments, or how do you parameterize the build process? Because if you think here, so here we have a particular model, for example, the Finnish model right here, but the parser eventually will have something like 80 models, and you don't want to have 80 Docker files for these 80 models. That would not be really sustainable. So what you want to do is that you want to give a parameter to the Docker itself when it builds this this image, and that's how this is how you do it. So I can just define that, you know, when I'm building this image, I have several things that I can parameterize. Most importantly, the model name, the pipeline name, the max hars, and also maybe the port on which it will then be listening. I don't think that's super important to parameterize because that port is kind of within the image. So it can just be hard coded, but let's just make it an argument because we can. So these, mind you, these are not shell variables. These are not, this is not something that's in shell. This is a Docker thing. So this says that now Docker, when it's building this image, it's aware of there being argument, model, pipeline, port, and so on. If I want to set these to be environment variables kind of in the shell that runs in the image once you launch it, then this is how you do it. So there is this env, that's basically a Docker instruction to instantiate to set a particular shell variable when it runs, when it then actually launches the image. So this is parameter of Docker when building, and this is a shell environment variable that will be set by whatever startup scripts that Docker generates for the image. So this is a super important difference. So here I just set these environment variables, and those are the variables that then the Flask, when it launches, actually reads from its own shells. So this is my way of passing parameters from the command line when I build the Docker image all the way to basically the Flask process that will then be running the parser. I hope this is clear. So now we have set all of these environment variables. Then there was a thing that needs to be done when you want to run the parser is you want to fetch the model. So you run fetch models py and give it the correct model name. This is something that you saw when I was showing you how to run the parser. And this is done only once now when you are building the image. And that means that the model, which is about 0.5 GB, will actually be part of the image. It will be stored in the image. And when you distribute the image, it will be there. So the upside is that every time the parser image is launched, it's kind of instantiated into a Docker container and kind of starts. It does not fetch the model from our poor little overloaded web server that serves these models, and it's fast because the file's already there. The downside is that the image file, the Docker image file, now has this 0.5 GB sized model. So every time someone's pulling this image file, or whoever is hosting this image file has to host this model for you. So this is something that, you know, this basically grows the size of the image by 0.5 GB. And it's kind of up to you how you want to design the image file. I also could have done it so that I would have made it happen that this model gets downloaded when you launch the image itself, which would make the image file itself much smaller. This is the point where the parser is basically installed and ready to go. So here are a few final things that you need to do. This is something that Juhani had in this example. So if this Docker is supposed to be listening on a particular port, then you should give the instruction to expose that port. So this basically says that once launched, this image will be listening on port 7689 on its own internal port 7689. If I launch 20 of these images, it doesn't matter. Every one of them internally has port 7689 exposed, and then Docker itself will have to figure out, or well, you will have to tell it how it should map these internal image ports into ports of the machine on which the image is actually running. And these two last commands are basically way to run the Flask. So I have to tell it which Python script in the directory has the Flask application. So it's this tnpp serve. That's the thing I was just showing you, which has the which is basically the Flask application. So I just set that as environment variable because that's how Flask likes to have it. And then there is this command Flask run. I tell it, okay, bind the public port, which means the port of the running image. And I tell it on which port I would like it to run. And then it basically starts the application and starts listening. And that's basically all that needs to be done. So these lines that I just showed you is what Docker will step through one after another when it's building the image, and when it's done, the image is kind of ready, and then you can instantiate it in different containers. So if we now run this, I should have it somewhere in here. I will just move this. Okay, so I have to make my window a little bit smaller because it's covered by the Zoom control panel and I couldn't see it. So here's the Docker build. That's already super easy. So I just say, okay, build based on this Docker file.server. In case you have a number of Docker files, then -f is how you tell it which Docker file it should use. And then I will tag it as tnpp-fi server :latest. That's just a tag. And this dot in here means that this current directory is the context in which the build will happen. So, so that is what the copy kind of refers to when you say copy a particular file into a place on the image. Then the from part, so where the file should come from, is this dot. You could specify there something else as well. I mean, you could have a particular directory somewhere on your machine that has the exact environment you would like to have for Docker to build the image. This is maybe a bit mind-bending what it means, but if you put there dot, then it just means it will be copying from the current directory where you are. Let's see if this runs. So now this is the kind of unfortunate part of Docker build process, when it basically sends everything that's in this dot in your current directory to Docker server. And if you have a lot of files there, you know, while you were debugging stuff, you can have some old stale models there, then it submits everything. It can be easily a few gigabytes worth of data. And then it runs the build process. Again, for me, this now doesn't take any time at all because I already did that. So everything is cached. And you see that it runs a step and then it produces this layer, which I was talking about in Juhani's session, question answers, and gives it some sort of a hash ID. And if I change something, it would start rebuilding things, and building this Docker image with 0 cache takes about 10 minutes, mostly because of the pip install requirements, txt. But okay, I did this. So I can do something like Docker image ls. Now you see many more images in here because I'm running this on a server where we actually run a lot of other stuff inside Docker. But here you see, this is the this is the latest I ran. And you see that this is like 40 minutes ago. Now, the reason for that is that everything was cached. I did not change anything. So it basically resulted, the final layer is actually the image. You see the final layer is F83DC9, and here we have F83DC9. If I now give it a different tag, let's just say latest 2 and run it, this will again submit things to the daemon, but after that, everything should be cached. So the compile should actually happen easily. Let's wait for just a tiny little moment. Yep, and now I do image ls, and here you see I'm having here this latest 2, but it still says 41 minutes ago because it basically came straight from cache, and the image ID is the same again. So I just basically, the result is that I have the same image with 2 different tags. So there is this caching mechanism in Docker is something to be like acutely aware of when you are working. That, for example, when you run a build command, then it's not necessarily that here appears an image that was created 3 seconds ago, because if it all comes from cache, then it just results in the same image ID. And once it's built, we can run it. Here I will just show you a way that's easy to run if you want to debug things and you want to be able to quickly just Control-C and kill the running image. And I will tell you something about the port mapping. So this -IT means, I believe, interactive TTY. So that basically says that you do not want to run this image in background, and you want it to open a little terminal. So T is TTY terminal. Then the next parameter that you have is 5000:7689, and that basically tells that I would like to bind port 5000 of the machine on which this image runs to the port 7689 inside the image. And so that basically establishes the mapping between the server port and then the port of the running Docker container. And here is which image I actually want to instantiate, so I can just give it a tag. You can do many things. You can also give it the hash, and you can only give it part of the hash. So I mean, I could also write here this F83DC. I think that should be enough. Let's hope that's how it works. Yep. And now it actually started it. This is, I mean, this hash thing in here is, I think, quite useful trick to know. This is also a reason why I rarely give names to these running containers, because I can always just pick the first 3 characters of the hash in here, and you can always refer to a running image like that. And here the parser is running, and now it's ready to go. So let me go to the parser. This will crash now, but basically this is how you should be going. If I was on the server that's actually running this image, this would have worked, but I'm not, because this runs on a separate server, and now I'm here on my own laptop. So I need a way to go to port 5000 of the server, which is where the actual image is mapped. And probably you know that I can do it with just SSH tunneling. So I basically SSH to that same computer again and say that I want my laptop's port 5000. So that's the first 5000 in here, mapped or tunneled into that server's, that's the local host here, port 5000. So I just run this and go here, and here is the parser running. So it's right here. You recognize this in here because that's actually the error message that was coded in Flask. And I can put here text equals, I don't know, minulla on kissa, I have a cat, dot run it, and here I've got the output of the parser. So this is kind of what it takes to write the Docker file, wrap it, and wrap the parser in a Docker file, build the image, run the image, and make the ports visible for somebody up in the outside world. So here you see that I'm on a quite different machine. One final thing, I'm overshooting my schedule. And because I sort of started it with this -it, then it just keeps running here, and I can Control-C it, and this will kill the running image. So this is super useful when you are debugging things, because I see the actual output. You see here I see the Flask standard output. The final thing that I want to yet show is how do you pass the arguments when building Docker. I made sort of a big deal out of having these arguments in here, but I didn't use them because they all had the same, they all had the sort of default values that were fine with me. But I can do something like this: build arg model equals, and I think it said phi ddt dia. Now I'm actually giving Docker an instruction to overwrite the argument model. So it won't take the default that's in here, but it will take whatever I have specified here on the command line. Unfortunately, we only have one model, so I have to put there the same one. But if I now were to hit enter, then it will basically just rebuild the same image again, because nothing changes. The argument didn't really change compared to what we had previously. So it should again grab everything out of cache, unless I'm completely mistaken. So when you are building the image, then you can just with this build arg, and you can put there as many. You see now it grabbed everything out of cache. But if I put here something else, like some different model name, then let's see what happens. It should basically die at some point because there is no such model under this name. But it should grab something out of the cache basically until step 19, which we see in here. It should be able to grab the cache, and after that, it should be grabbing the model. But yeah, oh, sorry, step 15 is when it stops, because that's the set the environment variable. So that's the point where you sort of diverge from the cached layer and start doing something else. So here we now start building from the point where for the first time the model is actually mentioned, because this is now what we changed. And that crashes now because I gave it a model that did not exist. So this will now crash and will fail to actually build the image. So this is how you can pass the arguments when building the Docker file, and this build arg can be repeated on the Docker build command as many times as you want, and you can put there as many arguments as you ever want. But that's basically it. So I think with the commands that the commands that I was now typing in, you actually have them in the slides that Sebastian sent you, and you should be able to replicate everything that I have done in here. I'm running it on a completely standard computer with nothing fancy installed on it. So that's pretty much what I had for this one. And sorry, I have slightly overshot the schedule that we have agreed. Continue, and I just have a small example of how you can run the parser, which I showed in the previous session. How you can run it with GPU acceleration in Docker. So let me just share my screen, and here are few links. I guess the hardest part, that's the one I cannot show because I've already done it on the machine on which I run the Docker. But I mean, you need to do few things to actually get the GPU support into Docker. It will vary system by system where you actually have Docker running, but the link is here. I added one slide to the slide deck which we had on Monday, and here is pretty precise instructions for all flavors of systems you might be running and that are actually supported by the NVIDIA extension to Docker. And by my experience, basically you just run it and it pretty much worked out of the box. So here is the instructions, I believe, for a Debian-based Linux. And you basically just, add this NVIDIA repository, and then you install NVIDIA Docker, restart Docker, and you're done. So that's pretty much my experience. I'm pretty sure here we'll have other people who tried something like this and have a traumatizing experience doing that. But for me, this pretty much worked. So if you have a standard dish system, then you will find the instructions to sort of enable the GPU capabilities in the Docker server on this page. And then another, I think, quite important link is this one, which is a collection of images, Docker images that NVIDIA maintains and that are sort of tested to work. It's right here, containers. So here is containers for various tools and software that you can possibly need that are officially supported. Let's say that I need Torch. So I will look for one. Sorry, I think I should be looking here, Torch. And here is, for example, an image for Torch. I don't think it's the one I was using. Was it perhaps this one? Yep. I think this is the one I was using. So that is a good image to base your own Docker file on. And probably it makes sense to actually go through all this list that you can see. This is everything is basically PyTorch. That's the one I was looking for. I thought it was looking a bit strange. Here we go. That is the one. So it says that this is a PyTorch image with GPU acceleration, and this is sort of compiled and supported by NVIDIA. So you have a pretty good chance that it works. If you try, for example, start with just the CUDA image that NVIDIA distributes, and then you simply apt-get install Python into it and install Torch, then the GPU support in many cases actually fails to work, because you can imagine that this is a little bit of a fragile setup that is working here. So when I was preparing the example for today, this is where I went, and this is where I started from. So I looked for a sort of official NVIDIA supported image that would have PyTorch on it, because that is the best chance for you to actually get something running. But after that, it's actually not very difficult anymore. So the only thing that I actually needed to change in my example is the from statement in the Docker file. Let me show it to you in here. I can have the problem that last line of the terminal is covered by zoom controls, so I cannot see it myself. All right, here we go. So I just made a new Docker file. The previous one was called Dockerfile server. This one is called Dockerfile server GPU. And you see that previously this was saying, I think Python 3, and now it says NVIDIA PyTorch 2006 Py3. And that is the exact thing that was in here. I had to use a smaller version. This is, or like older version. This is one of the things where you will probably acquire a little bit of gray hair when you are doing this, because when I tested with the very latest PyTorch NVIDIA image, I got an error message that my NVIDIA drivers on the server on which I'm running are not compatible with the NVIDIA drivers that are assumed by this image. So that's somewhat annoying, and you don't want to mess with your NVIDIA drivers all too often. So my solution was to go to the tags in here, and then I simply picked an older tag. I knew that our server that runs this image is Ubuntu 20.04. So I figured that maybe if I take one from June 2020, so that comes few months after the 20.04 came, maybe there is a good chance that it will actually work. So that's how I came up with this 2006 image. I basically try to match it with the drivers that I know that got updated around then. And after that, it actually started working. So with these images, you have few more points of uncertainty, and it might happen that things will not work on the first try. And often it is down to different versions. But there was a very nice error message that basically led me almost directly to the solution. When you launch the image with the in the interactive mode, so that you can actually see what it outputs, there was when you started, there is this nice list of what it's doing and whether it succeeds or not. And there it basically said, look, you are having two old NVIDIA drivers and this image does not support them. So you will have to upgrade your drivers or get an older image. And I didn't want to update my drivers, so I got an older image. So that's how I ended up with this. But other than that, nothing is changed in this Docker file. It is exactly as it was before. So the change was absolutely minimal. And then another thing that I needed to do is that previously I had this Docker run example, command, and now I have NVIDIA Docker run. So there was another thing that I changed when I started it, that basically I think that is more or less an alias for Docker with particular parameters. You basically if you want to run something GPU accelerated, you have to tell Docker which runtime to use. And I think the NVIDIA -docker command basically does that. And then it just runs Docker as usual. So not Docker run, but NVIDIA Docker run. Then I added this RM command. That's actually quite nifty. It deletes the image when you are done, so that basically you don't have to do it and you don't accumulate too many kind of stale images in your cache. But other than that, this is exactly the same. So if I now run it, I wonder what this LE, I think it's like this one. Yep. Now it will start it. You see, this is the output that's that the image has at the beginning, and it basically informs me whether, you know, which drivers it found, which drivers it did not find. And this was the place where I got the error message that the drivers are incompatible, after which point nothing worked. But here I have it. Now it starts the parser. And let's just wait for a little moment for it to load the parser model. And this is an NVIDIA SMI command that's running on the server, not in the Docker, but on the server, which runs the Docker daemon. And you see that here is, you see the parser actually loaded in here. So that means that it actually did reach all the way to the graphics card, and it actually is physically now located on the graphics card. So this is basically a way for me to check that everything worked fine, and the parser actually gets to see the graphics card that it should. And because it is loaded on it, then everything seems to be doing fine. So as you see, that's actually, and now I will kill it and then it should disappear from there. So as you see, this is not super difficult to achieve. Probably the most involved part is making sure that the NVIDIA extension to Docker is correctly installed on the server, which runs the Docker server, and then making sure that you are working off the correct image. And that's pretty much all there is. If you then try it, you can basically run some of these images. We can try it. I mean, they behave exactly as a normal Linux would. So a good way to kind of test and debug things is if I just grab the name of the image and see if I can make it work. So this is the name of the image. And if I do NVIDIA Docker run remove interactive terminal image name, and I will run bash on it. Now this is not something I would have tried, so if this doesn't work, sorry, it's always a little bit exciting, but here I am now running bash inside that image, and I should be seeing my graphics card, and I do. So this is a way to sort of easily debug and test things for the NVIDIA accelerated Docker. And now if I just exit this, then the image will be deleted and there is no trace of it left in the system because I used this --remove tag. And that's pretty much all I had to show for the NVIDIA acceleration. There is, of course, parameters or run arguments when you start the Docker. If you run NVIDIA Docker, probably with help, you can specify how many GPUs and which GPUs it is allowed to see. Let me see if I can find it in here. I can't find it right now, but there is a way how you can specify how many and which GPUs will actually be exposed.
Maybe in the NVIDIA Docker build help,
or actually run help, right? So
yeah,
that was a good point. Thank you. I saw it there, but now I can't find it. Obviously, here. GPUs, GPU request, GPU devices to add to the container, and all to pass all GPUs. So I think that you basically can just add a list like 0, 1, 2, and so on if you have many GPUs, or you do all. And I think that is the default because I did not use that parameter when doing the Docker run, and I still did have access to the GPU. But I can't test this on this machine because this machine only has one GPU. So there is this kind of control, which is of course very useful, and I think that was documented in the image documentation itself. Here you can see it. Here is this GPUs all. So that's that's where I have gotten this information from. And this is probably the best place to go for help if something doesn't work. So I think, Sebastian, you can stop the recording now. This is